There we go. So what we're going to do today, the goal is to learn how parallax measurements work. And remember, we said before, measuring distance is one of the most important measurements astronomy makes. Everything that we know about the universe is kind of dependent on measuring how far away things are. And you'll see that later on in the course. So we're going to see really the only direct way of making a measurement to distant objects in space is through something called parallax. And this is the thing that we did where we put our finger out in front of us and we closed one eye and opened the other and we saw it shift back and forth, right? So that's what parallax is. Now remember, the ancient Greeks thought that the stars were like all fixed in the sky because of the fact that they didn't see parallax. They knew what parallax was, they didn't see it because the stars were just too far away without a really, really good telescope and waiting until the entire orbit halfway around the sun can you actually tell that parallax is happening. So let's talk for just a quick second about how parallax works astronomically compared to how we might do it on Earth like a surveyor, and then we're going to dive into the lab. So the first thing is that all of this is really just based on SOHCAHTOA. So if you've had some geometry in math class, all of this is going to look pretty familiar. So let me draw this out for you. We've got a star here, okay, that we want to measure the distance to. Here's the sun, which is our star, and here's the Earth making an orbit around the sun, okay? So if we draw a series of circles, we can draw one circle with the star at the center, okay? And we can, in the sun out here on the end of the radius, and then we can draw the Earth going around the sun as another circle. Then what we can do is we can set up a triangle, and you can see that this is a right-angled triangle here with the sun at the right angle. So what we're going to be using in this to pull this off, slide this up a little bit, is we're going to be using the formula, the tangent of the angle equals opposite over adjacent. So if you've had geometry, that looks pretty familiar to you. Now, in terms of my picture here, the adjacent angle, or the adjacent side, is here. It's the actual distance to the star. The opposite side would be half of the Earth's orbit. Now remember, the Earth-Sun distance is an astronomical unit. And so in this, that is the distance, 1 astronomical unit, okay? So the other thing that we need is our angle, which is right there. We need the angle that this makes between a right angle and a measurement from over here. So in order to pull that off, you actually have to take a picture from both sides of Earth's orbit around the sun. So we need a picture over here too, okay? And then we'll get this whole angle. The parallax angle in all of these is half of this angle. You can see if I make the other angle over here, we're going to be taking half of our angles. So throughout the activity, we'll have to divide by 2 when we've got the angle. Okay, so just to kind of lay this out again, this is the actual formula that you might use on Earth if you were a surveyor. But you can kind of cheat it a little bit if you're doing astronomy. And the reason is that the star is so far away compared to anything we'd measure on Earth, okay, that we can kind of make an approximation and not have to do the tangent of this angle. We don't have to take the tangent of it, which makes the equation even easier. So if you're wondering how that works out, you kind of have to put your calculator in radians and then take the tangent of a very small angle, because this angle here that we're measuring is so teensy-weensy small. I mean, we were talking fractions of a radian, like really small, and radians are smaller than degrees. So it essentially works out that even if you take the tangent of it, it's the same number. So taking the tangent of it is kind of useless. So we can simplify the whole equation and use what's called the small angle approximation. And so our distance to the star, as measured in parsecs, is going to be the radius of Earth's orbit, which is 1 astronomical unit, because our whole baseline here, and you'll hear me use the word baseline, our whole baseline is 2 AU, 2 astronomical units. Half of that's 1, okay? So if we take the radius of Earth's orbit, that's 1 AU, over the parallax angle. So you're gonna see this equation written like this, D equals 1 over P. Ta-da! It's such a simple equation once you go ahead and take the fact that you have to tangent anything out of that. Because the angle's so small, we don't need to use the tangent. Although on Earth, if we were doing it, we have to. So for lab, since I've got this set up in distances that are really short, we will have to use the tangent equation, okay? We can't approximate with a small angle. And that's gonna be one of the questions on the back of the paper is why that is. And it essentially boils down to the fact that our distances are too short here. This approximation of not having to do the tangent only works for objects that have a very, very small parallax angle. When the angle you're measuring is really tiny. None of our angles are going to be that small. I mean, this is like fractions of a radian. And we're going to measure in degrees when we do this. I'm sorry, when we do this. So we're going to do it kind of like a surveyor would. Okay, I gave you some units down here. You'll want to keep referring back to this. I just used the unit parsec. What a parsec is defined that if the parallax angle is measured in arc seconds from Earth, okay, at 6-month intervals, then the distance to a star, that's on either side here of the sun, the distance to a star is in parsecs. So 1 parsec is the distance to an object that measures 1 second of parallax. Get it? A parsec. So that's where the unit comes from. Because it's kind of funny when you see that. If you've ever seen, if you're a Star Wars fan, you've ever seen that, and the famous scene, I can't remember how it goes exactly, but where they're talking about making the Kessel Run in like so many parsecs. Well, parsecs isn't a time unit; it's a distance. So the whole scene doesn't make any sense if you know astronomy. But so be it, right? So I gave you some translation, some conversions here. You'll need those. Here's how you do percent error, because we're going to do that. Okay, it's all pretty basic stuff. Let's set up the experiment. Basically what we want to ask today, the question we want to answer is how parallax behaves as you get farther away from the object you're looking at the parallax, and how your accuracy behaves when you have a long baseline versus a short baseline, when you have an object that's closer versus an object that's farther. And so you probably already kind of know the answers to some of these questions as we go. The first thing we're going to do is we're going to use our eyeballs as the baseline. So instead of half of Earth's orbit, okay, we're going to go ahead and use right eye and left eye, just like when you'd open and close your eyes. And we want to know the parallax, which is just going to be subtracting the 2. Okay, how much does it parallax? I'm not going to make you divide this by 2 because it doesn't really matter. We just want a relationship, okay? So let me show you how we're going to set this up. Go on a little trip over here. Okay. Going to be my demo. Got this set up here. And yeah, you can come over to the side. I've got the ruler, the meter bar here, right in the middle at 50. Right on my 50 centimeter line, okay? Oh crap, would you grab my computer? Thanks. Left the other class behind. And this is all set out like this. I've got a piece of tape that goes every 5 centimeters. So measuring all the way out to 30. Okay, we'll try and get everybody in here. There we go. You guys kind of see my setup there, I think. So we've got a piece of tape that measures all the way out every 5 centimeters out to 50. And then we've got 50 on the meter bar there. It's all set up at right angles here. So the next step is going to be to put our nose right here, okay? And we're going to put this pin, which is going to represent our star, at exactly 5 centimeters. So then we'll open and close an eye without shifting our head as much as possible and read where we see the pin against the meter bar, okay? Once we get that number, we have to subtract. We've got to subtract the smaller one from the bigger one to get the whole parallax angle, right? Because this isn't starting at 1 down here or 1 down there. You're going to get 2 sides when you open and close each eye. So it's going to look like this. Like, let's pretend here, looking through eyeball 1, looks like that. So you'd line it up there and you might say, oh, it's like 43 or something. Looking through eyeball 2, and you'd line it up there and you'd say, oh, it's like 58. And then you would subtract the 2 to get your parallax angle. And we're gonna see how that behaves as we move this thing farther and farther. So the star is getting farther away. How is parallax changing? Let me give you a quick example there. It's almost all the way out to 50. Look at how much the parallax moves. Right? So you can really easily see what the relationship's gonna be right there. So we got some data here, and your trend, when you plot this out, we have distance in centimeters here, and we're gonna have parallax in centimeters going up. You could probably space this just by ones. I spaced it out a little bit too much because our highest amount here for parallax was 36. So we're graphing the parallax here, okay, and our distance in centimeters right here, okay? So when you get done with this, you're gonna see a line that should pretty much approximate going down like this, okay? And hopefully you guys all got that. What you're experiencing here is the relationship between parallax and distance. So as distance increases, what happens with parallax? Does it increase or decrease? Well, as distance increases, parallax decreases very quickly with distance. So our highest parallax values, in other words, the easiest ones to measure, are gonna be at the nearest distances. This thing's gonna shift a whole lot more if you're closer to it than if you're farther away from it, which is why the most distant stars, there's no way, in fact, any star more than about 100 parsecs away, we can't measure distance to this way. This only works for nearby stars, because once they get too far away, there's no shifting. You can't see anything move. Okay, so what was our baseline? What do you think our baseline was? Our baseline in this activity was the distance from eyeball to eyeball. So we're talking like what, 6 centimeters or so, depending on how wide apart our eyes happen to be. So the distance in the activity was, the baseline was the distance from each measurement, which was eyeball to eyeball for me, okay? What's the relationship between the distance to a star and how large its parallax is? So the farther away a star is its parallax bigger or smaller? We just talked about that, okay? Next up, we're gonna do some conversions here. We're going to do some calculations and some conversions. So we're going to take myself back on my stand here. There we go. And I'll do this first one with you here. Actually, it might be kind of hard because I have my calculators on my phone. So these are real stars in the northern hemisphere. Their parallax values are presented below. Complete the table by calculating the distances from Earth in parsecs, just as astronomers do. Then calculate what these values are in light years and kilometers. Okay, we'll put our answers in scientific notation where we need to. Let's go ahead and do one here. So I don't have a calculator to show you how to push the buttons, but we're using this formula down here, we're using the astronomy one. So distance in parsecs is just 1 divided by the parallax. How about that? So this is the parallax. Take 1 divided by that, and if you do this right, your first answer here should be 1.32, and that's in parsecs. Okay, so try that out. Make sure you can do it on your calculator. You can do the rest of these because I'm going to ask you a question about this on the quiz. Now, to convert the parsecs to light years, I gave you some conversions down here. If 1 parsec is 3.2 light years, okay, we're going to have to multiply by that, right? So take this number and multiply that number. And if you did it right, you should get 4.25 light years. Okay? Not writing my units, they're right up top here. Now we want parsecs. Well, we want light years. We just did light years. Sorry, we want kilometers. So we're going to take our original measurement again in parsecs, and we need to multiply that by kilometers, but don't forget the scientific notation here. Okay, so multiply those two together, and we've got 3 sig figs here, so we could go ahead. It's going to come out to 10 to the 13 there. So go ahead and work the rest of those out and get all your answers here because you're going to need them for the quiz. We're going to find parallax from two photos. So in reality, when astronomers do this, they're really taking a photograph from one side of Earth's orbit and then the same photograph from the other side of Earth's orbit. And what's going to happen is there's going to be a bunch of stars that don't move because they're the background stars. They're the stars that are so far away they can't move. We don't see them parallax. So we're going to look in these two pictures. Can you find the star that has actually moved? Can you see the one that has actually moved? If you look close, it's this guy right here. That one in this picture is way the heck over here. See that? Now what we need to do is we need a measurement. I don't want a measurement from here to there. Those are two different pictures. What I want is a measurement of how far it's moved. So what I need to do is I need to measure its change from a star. So what's easy, what's convenient here is right now, see how it's lined up with this star? And it didn't move from this star in this picture. So all I really need to know is how far it's changed position. So I need to measure from here to here. I need to know how far that is from there to there. Okay, so if I measured from there to there with a ruler, I'm just going to go ahead and tell you in case you don't have a ruler at home. I got, when I measured that, where can I write this? 29 millimeters. When I measured from here to here. So that's how far it shifted from where it was in this photo. So this is the December photo. This is a June photo. Okay. So this is the parallax that that star has traveled. So now we're going to put that right here, 29 millimeters. Okay. And I want to convert that distance to arc seconds. Okay, using the scale. So I gave you a scale here. This is a pretty easy conversion. I have 29 millimeters times in a line, just like we do dimensional analysis in chemistry. My units are arc seconds per millimeter. I want millimeters on the bottom, 1 millimeter to 0.01, don't forget the 0, arc seconds. So that's the symbol for arc seconds. Okay? Somebody do that, see what you get. What did you get on your calculator? So figure that out, and then that is what you're gonna write right here. Okay, that's your distance in arc seconds, whatever you get here. So you're gonna multiply by that. Let's divide by 1, that's no different than doing nothing. That's seconds of arc. Now in reality, stellar parallax is half that. So in this question, you have to take half of what you got in your answer, right? That's the whole angle, so just divide by 2 to get this answer. Okay. Now to calculate the distance in parsecs, just use d equals 1 over p. So you take 1 and divide by whatever you got here. And that's going to give you this answer. Okay. And then really quick, why are those stars in the background not seeming to parallax? It's simple. They're just too far away. They're so far away that you're not going to see a parallax on them at all. Right? There. So what we've got is our first star way over there on the aquarium, and we have a baseline here that's exactly 1 meter long. And I wrote that on there, 1 meter baseline to star B. And we've got a mark on either side here, and the tape extends out past the mark. So that mark to this mark here is exactly 1 meter. Okay, and the center of this thing is lined up with that star on the aquarium over there. And we want to see if we can figure out the distance to that star using this baseline. So I've got some very specialized equipment here for you to use. Grab one. Uh-oh. Where's it gone? Oh no. So what I've got here is a fancy instrument made out of a protractor and 2 paper clips. that we can sight down and line up with that star and try and get the angle to. So on this right here, so you're going to line up the center point of the protractor with the tip of that line, okay? And then we're going to rotate this to where we need to rotate it, so when we look through it, we can see paperclip to star. Then what we need to read off, the smaller angle out here. Whether it's on the inside or the outside, we need the smaller angle, okay? Because we're trying to get this angle to the star, and it's going to be out against this front edge of the tape. So let's do this first one here. I'm gonna try and line it up. Okay, so I got it lined up. Make sure to double check that you're on the tape still, okay? And then we look over here. You still see it in there. And we're at, see here, 70, 80, 1, 2, 3, 83 degrees. So I'd write that down. This is star B, 83 degrees. That's my angle, okay? See that? So every one of these baselines is 1 meter. 1 meter, I just wrote that at the top, except for star D, which is gonna be 6 meters. I'll show you guys this. So we just set up angle B now. It doesn't matter which one's A and which one's B on your paper. And right now we're at 80, I'm using the smaller number again, 81 it looks like. Right at 81. So you'll write that on your paper. And those should be pretty close. I mean, they probably won't be exact because of, well, we're measuring with paper clips and because I probably didn't put the tape on there perfectly. Okay, so now that we've got those two numbers, now we can go ahead and do our first calculation. Okay, so you can make all your measurements first, or you can do your calculation first, but I'm going to walk you through a calculation. Okay, let's explain this measurement here. Okay, looking at my triangle that I've got here, what I'm going to need to do in my calculation is I'm going to need half of my baseline. Well, that's easy. All my baselines are a meter, so it's 0.5 meters, right? And then my units are going to come out in meters. So first, let's figure out our parallax. So we've got our first star here, and we're going to figure out the parallax. So in this situation, we took a measurement from here and a measurement from here. So we're going to use some real simple geometry here to figure this out. What we want to know is distance D, but to start with, we need to know what P is. That's our parallax angle. So let's figure out C. We've got these two angles, and A plus B plus C equals 180. We could rewrite this equation, right? C equals 180 minus A minus B. So if we subtract our two angles from 180, we'll have C. So you're going to take 180 minus these two, okay? And then that'll give us C. Then we need to divide by 2 to get P, and we will get our parallax angle right here, okay? So take a second and go ahead and do that, because the next step is going to require an equation. And you're going to need a calculator that will do tangents. So,
did you say divide C by 2?
Yes, you're going to have to divide C by 2 to get half of it, because your parallax is actually half of this angle. It's half of this C angle. Remember in the original drawing. Okay, so the equation is pretty simple. If your baseline is 1 meter, you're going to take half of that. So 0.5 divided by the tangent of your parallax. So whatever you got down here for parallax, take the tangent of that. That's really simple. Just hit the tangent button after you type in the number on your calculator. Okay, and you're dividing this by the tangent of your parallax. That should give us our distance in meters. See what you get. Okay, so I've got some new data here for you guys. I'm going to work through that star B again here because I accidentally wrote down the wrong number, wrote the same number twice, so I'm going to work through it again for you here. So copy down this data for your lab, and then you're going to calculate parallax, distance, and percent error. You can't do percent error until I give you the actual distances to the stars. So we made these measurements, we got the two angles. We're going to figure out, like for instance in star B, we're going to figure out what the parallax angle is. So to do that, I need angle A and angle B. And it's just like making a triangle here. So angle A, angle B. Well, since A plus B plus C equals 180, I could rearrange that equation. As long as I subtract A and B from 180, I know what C is. Well, C is not parallax. C is twice parallax. I need to divide C by 2 in order to get my actual parallax angle. Okay, and that's going to be in degrees. So when I do that and I divide by 2, subtract both of those from 180 and I divide by 2, I get 8. Okay. Now, to work out what the actual distance is, this one came out to 3.6. You're going to get your distance in meters equals half your baseline. In this case, half of a meter is 0.5, okay, divided by the tangent of the parallax. So just hit the tangent button on the calculator for the parallax. Okay, divide 0.5 by the tangent of your parallax, and it should come out to 3.6 if you're doing it right. Okay, in a minute we'll do percent error. Work out the other ones here for each of these stars and figure out your distances. Okay? Most measurements are not going to be exact, but I want to know which ones we got the closest on. So here's some answers. Star A, its actual distance was 2.0 meters. Okay? So when you're figuring out percent error, see how close you got to 2.0 meters. Star B, its distance was 4.0 meters. So work out your percent error using this as the actual. Star C, its actual distance, 11.2 meters. Star D, its actual distance, 14.10 meters. And this is star D as well, but using a different baseline. Okay, so work out your percent errors there. See which ones you got closer on.